Last lecture we have seen continuity and momentum. Today class is energy equations. So energy equation already you know people. It's used for calculating temperature of flow fluid. So the energy equation for temperature the flow fluid. Okay. So as usual we have considered three-dimensional fluid element. It's having an axis of z, x, y, dx, dz, and dy. So here to get the energy equation, I will apply conservation of energy. Okay. So conservation of energy starts from where? It's a start from thermodynamic first law. So before writing your examination, you should write your principle behind the energy equation. So principle energy is conserved. So more clearly I can derive this energy is conserved from thermodynamic first law. Change in energy equal to heat addition plus work done. Okay. So this is a general first law of thermodynamics. Now I will apply this first law of thermodynamics to this volume, a small finite volume. Okay. So first, and we can give a reverse statement of this first law of thermodynamics as the left hand side, rate of change of energy equal to heat addition or extract from one to the elements plus rate of order by the fluid element. So this is a general statement behind the first law of thermodynamics. Now I will calculate each term in the equation 1. Okay, for this fluid element. To apply first, I would like to solve the right hand side of the equation 1. So in the equation 1, first calculate the rate of change of work. Rate of change of work. So rate of change of work means you can simplify the force into velocity. So in general, work means force into distance, but here rate of change. That's why I differentiate the distance with respect to time. It has to change as a velocity. Is it? So here, this work done due to a pressure force and body force. Okay. So one can due to pressure, one can due to shear, the other due to body force. So first calculate what can due to pressure. So pressure I have considered acting in x direction. So how would we write the pressure term? And last lecture we have seen. So pressure at x and the area d1 dz. Okay, in the x direction cases this one and this one. So due to this pressure acting here, definitely it's fields changes. dx, this changes differential form. This pressure acting on this face in the differential change of with initial pressure. Okay. And the area is d1 dz. Is it? So this is the pressure acting in x direction. So now solve this pressure. I have considered towards the right hand side of pressure is a positive, and towards the left hand side of the pressure as to negative. Okay. When solve this, we will get d dy dz minus d dy dz minus dou v by dou x dx dy dz. This is pressure acting in x direction. Okay. So finally we will get minus dou v by dou x dx dy dz. This is for only pressure acting on the x direction alone. So we are dealing with three-dimensional body. So that's why I need to calculate pressure acting in a y direction, pressure acting on a z direction also. I can calculate the same thing for y direction pressure. Minus dou v by dou y, dou x, dou y, dou z. Similarly, for z direction, dou p by dou z dx dy dz. So finally, the whole fluid element fields this three set of pressure x, y, z. Okay. So work done. Due to pressure force, I can write because of from work done definition, we have calculated pressure force here, and we should multiply with the pressure differential with the elasticity component must be included, all the components of the pressure. So I can write this as dou u p by dou x, dou v p by dou y, dou w p by dou z. Is it? And then 1. Okay. So if you look at this equation, just I don't only for a pressure acting on a fluid element, but in our expression one saying I want to work on rate of work done by the fluid element. So I have to introduce my velocity component in the pressure force. Pressure force in the velocity means over the rate of work. Okay. So in the x direction, the u is coming Consider x direction faces again. I have to consider the x direction faces. So distance between two faces dx, and this is shear acting in this face. I mean, you can do it as A, B, C, E, F, G, H. Okay, this face and this face. You see? So this face I have extracted to in this area. So this is A, and here A, B, C, D, and E, F, G, H. So I want to calculate due to pressure acting on this face, means Px. So definitely all the face is shear. Okay, due to X pressure. Direction is so only one pressure acting, but three component shear is 3. So this is tau x. So x index indicates the direction of pressure acting, and this x gives a shear stress produced by the faces. Okay. You do x direction and a shear on this face, and area is again dy dz. So it must be differential changes. Tau xx plus dou tau xx by dou x into dx. This is a differential change of shear in this place EFGH, and the area is dy dz. Okay. So now we solve this. Again, I have to consider the sign convention here. So left hand shear, left hand direction acting is here. I have to consider negative, and right hand side shear I have to consider positive. So this is left direction, this is right direction. When you resolve this two component, we will get okay. So we will finally shear stress at x faces, x direction basis. So this is gives only pressure acting on x direction. In the 6 faces, x direction face only feels the shear variation. Now I can write similarly for y direction face due to a expression. Dou tau, dou x, dou y, dz. Okay. Similarly, for expression, dou tau y, dou z, dx, dy, dz. Okay. So these three shear variation takes place in the each direction. Okay. Dx, dy, dz. So now this is a shear stress at x direction due to Px. Okay. Now sum up the three shear stress here, we will get a x direction shear. Again, we are dealing with work done. So what are the must come here? So all the velocity now come here. Because of one force into velocity, we have found the shear force into that common velocity. So I have to multiply with that component. Is it? All the shear stress we have to rewrite as root tau xx. Root tau x1. Okay, this is a shear at x direction due to px, and u represents the x direction. Okay, because of this, we are dealing with work done. Okay, work done due to shear. Okay, so u is present at the x, and due to y, due to z. Okay, it must be multiplied. So again, shear stress at y direction due to Py. If you look at our figure, the last equation we have derived for when applying this Px here. So upper two faces, side two faces, and front two faces shrinks with each other due to a pressure. Likewise, pressure is acting in a y direction. Again, due to this pressure in the y direction also, it feels shear stress in all the direction, all the faces. So I have to account all the faces again with respect to y direction. Okay. So similarly, I can write this is a y direction. So that's why the v now I'm playing here, v tau, and it's a y. Okay, y direction. Through shear stress component we have seen when pressure is acting in the x direction. So due to the x direction pressure, all the faces feels shear stress. Like that, we have to modify and apply pressure when the pressure is applied in the bottom side. So definitely again all the neighbor faces feels a shear stress. So that I can directly write it as we manipulated here. So we know again the shear stress. This is equation number 2, and shear stress at the direction due to dz to w tau zx w tau okay, this is equation number 3. Now we have a shear stress y, z as well as x. Now summed up work done. Due to shear stress is summation of 1 and 2, 3. Okay. This is positive or negative? Positive or negative?
Positive.
Positive. Because of pressure only in a negative.
Negative.
Okay. And and temperature also gives a negative, then applying for here it has to change the positive. So it should be positive and negative state here correct. So finally we have dou u p by dou x. Sorry, dou u tau x plus dou u tau x y dou u tau x by dou z dou v tau yx dou v tau yy by dou y and dou v tau yx push here. Sometimes. Is it? Plus body forces over here. The whole bracket of dx, dy, dz. This is equation number 6. Now, the 6th equation speaks about total problem of our fluid element. Okay, so this we have to form. Now coming to equation 1 again, have to solve how the heat transfer takes place in the element, fluid element. Okay. The fluid element heat transfer, the heat is applied in here, Q dot. Okay. Q dot into the area, dy, dz, and after some distance it has to go out. Okay. It has to leave from our volume. I can write this as the same thing, Qx plus dou Q dot dou s to the dx. The area is dy dz. Okay. The same thing I have considered to manipulate the heat transfer in and heat transfer out as sign of. Towards the heat transfer is positive sign, towards the fluid element. Out of the fluid element, heat transfer is negative sign. I have considered. Okay. So negative sign. So heat transfer over its direction takes place only x direction. You are dealing with 3-dimensional effect, so I have to plug second or third direction of the transfer. For y direction, minus dou q y by dou y dx dy dz. For z direction, so total heat transfer in the fluid element, we summed up the all the direction and consider the equation number 7. 7, 8 and 9. Remember this? 7 plus 8 plus 9. I can write as capital Q equal to x so this is equation number 9. Yes, is it? So equation number 10. Now if you look at the equation A, we have found this part and this part. Still we need to calculate how the energy is expression. takes place due to this heat addition and the work done by the fluid. We have to find energy takes place in the fluid element. And before going to energy, I can introduce a Q dot X as, what is this? It's a Fourier law of transformation. So minus K dou T by dou X and Qy is minus K dou T by dou Y and Q dot Z as minus K dou T by dou Z. Is it? So okay, so second order term. Now, in the left hand side of the equation A, rate of energy changes. When speaking about generally energy in a fluid element, so there is if you look at the microscopic view, there is a vibrational energy, translational energy, and electromagnetic energy. So many of energy is present. So, but we are dealing with macroscopic. So generally, I can consider only atoms, molecules, and average kinetic energy. So energy changes due to the kinetic energy of molecules and internal energy. So internal energy E and kinetic energy of molecules I have considered as an average because of the dealing with macroscopic approach. I can consider as a V square by 2. The average kinetic energy of whole volume I have considered V square by 2 and internal energy of the fluid element. So generally energy I can define our problem in this derivation as E plus V square by 2. And if you look at our this whole volume, this is for only scalar. So we assume this is the spreading. This energy is playing in all the directions. Okay. So we have to contribute with respect to space and time. So energy, this in the box, giving the volume, it's a function of space and time. So to introduce the concept here, I can write it as a total derivative. Rho E by rho T and their mass. Okay. Dx, dy, dz. Is it? So total energy. So this energy, I can divide the mass of the volume into their substantial derivative. Okay. So substantial means there is a combination of local and space derivative. So our actual approach, the energy is changes with respect to space and time. That's why I introduced a capital D in substantial derivative here. So this is expression number 7. Is it? Now, if you look at all the number of equations, we have found all the parts in the available of equation A. Is it? So rate of change of energy, describes about equation 11, and heat flux is describes about 10. Rate of change of water in the fluid element in the equation 6. So substitute equation 11, 6 and 10. Is it? 10 to 8. Okay. You substitute all the equation 11, 6, 10 in the 8. We will get a of dE by dt and when you substitute the Fourier line here, I can rewrite it as a positive. Okay. K of
dt by dx
dou by dou x K of
dou t by dou x
dx okay. Plus dou by dou y K of dt by dy plus dou by dou z K of dt by dz
minus
good minus of
dou up by dou x
dou p by dou x
plus
dou
dou vp by dou y plus dou wp by dou z plus
and 9 components of shear. Okay. 9 components of shear. Dou x, dou x, dou u, dou y x, dou x. It must be y, is it? Then what is this? And I can introduce a first bracket from here to here, dx, dy, dz. So both volume will cancel there. So finally we have this is a energy equation for our current fluid element. Okay. So finally we get the energy equation like this. So already I said the energy equation, not only energy equation, all the equation we have conservation and conservation form. So if you look at the right hand side of this equation, what we have? Substantial derivative. So substantial derivative means it should be non-conservation form. So in order to get a conservation form, I have to destroy the substantial derivative. And why conservation form is important? Non-conservation form is not important in this particular problem. By writing CAD coding is very easy in conservation. As well as there is also again another formation. So strong conservation we will see after getting a conservation form of an energy equation. Okay, this is the final equation I think in the conservation forms. So in the left hand side of this equation is a substantial derivative. So I have to remove it to get the conservation form. Okay, I can write like this. Is it? So we have a row here. I should multiply with row. Okay. So we can consider the equation number. What's the analysis equation number? 12.
12, sir.
12. So now it's 13. So I have to calculate separate term in equation 13. Then substitute this value here. Finally, I will calculate and we will get conservation form of the equation. Okay. So we have to from 13 I can write differentiation of rho v. Okay. It's I can write this as a by using product rule here. Rho v by rho t plus e of rho by rho t. Is it? So what our expected value here? This one. So remaining you can send it in the left hand side. Rho t by rho t minus e of rho by rho t rho by rho t. Okay. So this is one of the results we obtained. Because of this value I have a substitute here. Then another result is requires from equation 13 this divergence values. So in the divergence values we call it vector identity. So I can write a divergence dot scalar of vector because of energy is vector scalar and velocity is vector. So whenever you have a dot product in the scalar and vector, I can write as a is it?
Yes.
I can derive from a vector identity. This is the primary maths you have studied in the P vector maths. Okay. M1 or so from here I can derive this term alone because of this term existing in the equation 13. Is it? So I have to extract this term in the equation 14. Okay. Extract this equation alone, this term alone. And substitute this one into equation 13. How can we write? Rho e by rho t equal to this term is rho e by rho t minus e rho by rho t plus and rho e okay. So if you look at this equation, I have to idea and rho e by rho t and this two term I can give it as a rho by rho t plus rho by. Okay. So if you look at this equation alone, this is
Continuity
by
equation.
continuity equation tends to 0 equal to 0 continuity equation. So finally we get substantial derivative now as we change as a ordinary, I mean partial differential So strong conservation form is writing string programming is easy, as well as it's maintain stability. So stability topic will be in the upcoming sections. So it's a very useful compare than weak conservation forms. So what we have derived in conservation form, this is a weak conservation form. So strong conservation form is I have to vectorize the, I have to vectorize all the non-conservation form to vectorized form. This is a strong conservation. So to develop a strong conservation, I have to summarize the conservation of the equation. So for complete the equation, dou rho by dou t plus rho v equal to 0, and x momentum dou rho u by dou t plus rho u v equal to dou t by dou x plus dou x equal to dou x plus dou tau x equal to dou y dou tau x by dou z plus dou dot x. It has already lesson classes. Now I have summarized dou rho v by dou t y momentum and the momentum okay, and energy equation you can write this equation. So only left hand side has been changed. So we have to substitute this value into here. You will get energy equation. Okay. So better left hand side alone I will write here. How would you write? Dou. So E stands for
E plus V square by 2. Yes, sir. Internal energy plus.
E plus V square by 2 plus operator E plus V square by 2 into divergent velocity. The right hand side again consider this capital X. Okay. So in the capital X, due to distance in bold I have to consider as X. Okay. Now you can extract the such a values. You mean to write a strong conservation is a simple one. So just we have to extract some values in a vertical column. We will get strong conservation. Now the general form of strong conservation I can write as a strong conservation as dou u by dou t plus dou a by dou x dou b by dou y plus dou c by dou z equal to h. Okay, this is general form, equation form. So where u is a solution to it. U is solution to that. Here is flex. Flex is Okay. B is the flux at y direction. Okay. C is flux at z direction. Okay. So these are the conditions. So what's important here is, so when you're dealing with CAD problem, not always not to be a three-dimensional. With respect to some of application we have to deal with the first one-dimensional, two-dimensional, three-dimensional. For example, if I want to interesting two-dimensional, okay, so directly you can ignore the C term because of the C term speaks about only mass flux on the z direction. So when dealing with the two-dimensional, so z coordinate, I mean variable doesn't change with respect to that dimension. So we have to ignore it. If it is your problem again free of body forces, you can again remove h. So just you have to solve up to here. Okay, so if it is two dimension. Again, if you hand into one dimension, you can again remove. So only property A is a mass flux variable with respect to external. It's a general thing in the one dimension. Okay. Now, how to extract the value of strong forms? So consider solution vector. So what are the solution? Before that, I give a format. Because so many of students struggle with write a strong form. So general form of write a strong form of information equation. You have to first write continuity equation in the vectorization form. Continuity equation you have to write first. Then x momentum, then y momentum, and z momentum. Finally, energy. So this is the general format to write a strong conservation. So first, continuity equation, what are the solution vector? U is the solution vector, already I wrote here. So what are the solution vector? So where is the time dependent variable? For example, look at the general grounding equation of a strong formation. So U is with respect to time. So those variables with respect to time in the continuity, momentum, energy, you have to summary in the U vector. Okay. So for example, continuity equation, the time is rho, the momentum equation rho u, y momentum rho v, z momentum rho w. These are the variables, time variables in the all the equation. And energy, this one. Okay. So if you look at the solution, time variable I have marked here. So you have to capture and substitute here. So the continuity equation time variable rho r1. Next momentum, rho u, y momentum, rho v, z momentum, rho w, and energy equation, E plus V square by 2. Okay, these are the pattern. The same pattern we have to operate in the writing A, B, C also. Okay. So A, you write A. So those variable presence with respect to x in a continuity equation. How do you write this term as I can write this term as dou rho u by dou x because of line x is present. Dou rho v by dou y dou rho v w by dou z equal to 0. So this is a general compact form. That's why I introduced the derivative. So A is only function of x. Okay. So you have to write x functions continuity and in the momentum x variable, x momentum x variable, and shear y and body force you have to give a separately. Then again when you expand this one, you will have the same thing. Okay. So how can I write it? In the
P by
rho u square plus p minus tau xx. Is it?
yes.
This is for only experimental. Listen. So here when you expand this divergent, you will get rho u into it's a divergent velocity. So divergent velocity means it's a combination of vx plus vy plus vz. Okay, so vx into rho u into u. Okay, u. Can simplify u plus v plus z. It's the best form for your number. So this v speaks about rho u plus v plus z. Okay, this is a divergence before rho u plus v plus z. And how can you develop divergence? Rho u by rho x plus rho u and rho v by rho y rho v w by rho z. Okay, so this is for the sum u square. Is it rho u square? So rho by rho x into here rho u square plus rho v rho w. So this term belongs to this category. Okay. Now tell me, you can understand now. So those are the x term and the x momentum. So this term belongs to x momentum. This term belongs to x momentum. This term belongs to x momentum. So that's why directly I have written only numerical terms. Okay, independent terms. Rho u square and pressure, on the right hand side, and shear. Okay, because we are dealing with here with respect to x alone. Is it? So when coming to b, you have to calculate the remaining y value. And when coming to a c, you have to bring a z value. And again go to a y momentum. Those terms are belongs to x in the y momentum. Did you understand? Those terms are present in the y momentum belongs to
x.
x. Okay. So that is the thing.
Rho vu minus tau xy
Rho vu
minus
minus
tau xy.
xy. That's all. Okay, then again rho
wu
then
minus
minus
tau xz.
tau
xz. Yes, sir.
Okay, both are same. Tau z x, x y, y x. So in the energy equation, so when you go to energy equation, there is a lot of terms. Okay, don't afraid and forget to elaborate the divergence form of equation. Again, apply here, you will get so many terms in the energy equation. Okay, so in the energy equation, those terms
minus k dot t by
u tau x and tau u tau v y z. Tau v
yx
tau y x
minus w tau xz minus
pressure, shear,
heat transfer term minus dou
q. Again q dot x. Okay, simply you can write it. If you want to use the substitution of formula, you can use it. Okay, this is belongs to A. So this is understanding is a little complex. It's a combined practice one time writing. Okay. So again, if you not understanding, again you are regular mode to this video, you will understand. So just those terms belongs to x. I have to separate the variables. Okay. So those terms belongs to y. I have to separate them as a b. So those terms belongs to z. That term I have to separate as a c. That's all. The simple thing only. So if you not understand, again you are regular mode of this video, you will understand. B, the same thing, the continuity is
rho v
rho v and momentum
rho u v
rho u
v
v
minus
minus
tau xy
tau
xy.
xy and here rho v square, is it?
Yes sir.
Then
Plus minus tau yy
tau y
plus p
plus
p
p alone, up or p
p
p
rho wv third.
up, it must be up. So this is see the second one is x momentum. Oh, only p. Okay. Then that momentum
Rho wv
rho
wv
w
v
v
minus
minus
tau yz
tau y. Okay. Then in some energy equation, those terms with respect to y and this term in the left hand side of energy equation. Okay. This term is belongs to y e plus b square by 2.
rho into e plus v square rho
Yeah. Okay. Then Vp plus
wp vp.
we are dealing with y.
Yes, yes.
So it must be V. Vp
Minus
and look at the board and tell me.
k
Those terms belongs to a y.
minus k dot t by dou y
That means there is a q
dot y.
dot y. Okay.
Yes.
Then
Minus u tau yx
u tau
yx
yx
minus v tau yy
v tau
yy
y.
minus w tau yz.
Okay. These terms all belongs to y. Is it z y? Okay. And if you look at the energy term, I write a divergent value here. So it's a V. V means I have said combination of UVW. Okay, UVW. So that must be included here for y term. It must be act as a V. Next term it act as a U. In z direction act as a W. So that must be included here. So A is a function of x. So it must be U. So B is function of y. So it must be V. Right here. So now again we have to write this form as a
minus tau zx y momentum rho vw y momentum vw minus tau yz.
Okay. Then
Z momentum
the third equation
rho w square minus tau z plus p.
Okay. And energy equation as usual, rho of E plus V square by 2 into W plus WP minus
K dou t by dou z, that means q dot z minus u tau xy xz minus v into tau yz minus w into tau zz.
So these are the just I have extracted from a continuity moment and energy equation. Just simple thing only. So just in the vector form, all the variables in the A is with respect to x. Okay. Here, so B is all the variable now here with respect to y. Now see all the variable with respect to. So we can find out A, B, C in the strong conservation boundary equation. Still one more term is available, that is H. So H means we have to summary all the body force existing in the continuity momentum energy. Okay. So because of you look at the right hand side of the equation, this equation having a body forces. So we have to summarize all the body forces into only one vector S. So that is H. So I can write H as so from the continuity equation there is no body force. Okay. Right hand side there is no body force. Continuity equation and x momentum rho f x, y rho f y, z rho f z, and in the energy equation, if you look at the energy equation, this is the body force of energy. So summary here for all the body force. So continuity equation 0, rho fx, okay, rho fy, rho fz, and rho fv. Okay. So this is a body force. So we have summarized vector acceleration form. So we have a strong conservation form of a equation. Now what's important? This is for writing CFD body basis and maintains long time of stability of vector. So I already informed stability concept I will take later. It's upcoming event, upcoming sections. And so in this set of conservation equation is weak conservation. So this is the weak conservation form, and this is the strong conservation form. Okay. So this is one of the important application in aerodynamics. Why strong conservation is important? So when dealing with the shock wave capturing in the domain, weak conservation form is failure because it doesn't give the shock location. Okay, when you solve a weak conservation form in the computation domain, we have to fix the shock. Okay, then only you can solve the variable behind the shock waves. Okay, what are the pressure, temperature, Mach number is increasing or decreasing due to the shock wave. We have to fix the shock. That is a shock fitting method. So whenever go to shock fitting method, weak conservation is enough. be going to a shock evaluation. So I don't know where is the exact shock location. So I have to calculate the shock location by using computational mechanics. So that time you can use a strong conservation form. So in the strong conservation form, when you apply it in the computation domain, it evolves the shocks. Okay, so shocks is evolved inside the computation domain. So these are the main difference between strong conservation and weak conservation. Okay, so tomorrow we will see when